Hello everyone, let us go through some of the concepts of deep learning. Here are a few mentioned over here. First is hyperparameters. Hyperparameter is basically those parameters that you can change a little bit to increase the accuracy of your deep learning models. Okay, deep learning neural network models. All right. So, which might that be? So, first is the learning rate, neta. We have seen this, right? Learning rate, neta. It determines the size of the step during the weight updates. Basically, if we multiply the losses or the change that we want in our change in the weights with neta, that tells us what how much of the fraction will we actually be using to update the weights. Okay, it's a very small learning rate results in conversions, while very large may overshoot the optimal solution. Okay, so if the learning rate is small, it will converge to the solution very slowly, whereas if it is very large, it may overshoot the optimal solution. So what we have to do is we have to uh, take learning rate in somewhere in between. Okay, it should not be very large or it shouldn't be very small. Then the batch size. Batch size is how many weights, how many inputs do you process at a time. Okay, if the entire samples, uh, if the it's the number of training samples processed before the model updates its weights. Okay, there can be mini batch gradient descents with smaller batches of 32 or 64 samples, or a batch gradient which uses the entire data set for each weight update. Okay, so depending on the batch number of training samples you use, it could be either a mini batch or a batch gradient descent. All right, and uh, uh, say you want to find the error. Okay, so mean squared error, we have seen the formula for mean squared error. We'll also, I guess, see it in a few moment, either in this video or another video, but let's go through the others. So the number of epochs is how many passes through the entire training dataset it takes. Okay, so if you have too few epochs, it might underfit, meaning that does not learn the model does not learn the patterns, or if you have too many epochs, then it would overfit, meaning it could memorize the pattern, and which we don't want, because it should perform on the data that it has not seen also. Okay, number of layers and the neurons per layer. So how many numbers you have, number of layers you have, that is the depth of the neural network, and the width, that is the number of neurons in each layer of network, is also crucial. Okay, more layers allow the network to learn more complex features but increase the computation time. Okay, then there is the dropout rate. Dropout rate meaning that means that how many of your not all of your um, layers, neurons are connected to all of the neurons in the next layer. Okay, so previous layer neurons are not and connecting all the neurons of the next layer. This is also, this is a regularization technique to prevent overfitting. It randomly deactivates a fraction of neurons during training. Okay, regularization is basically uh, the opposite of overfitting. Okay, so that the model does not memorize the data pattern. All right, and it performs well on the data that it has not seen previously. Okay, while training. Then there is weight initialization. Proper initialization avoids issues like vanishing and exploding gradients. Okay, so this Xavier and he initialization, it they basically tell you how what you should use as values for initialization of your data. For your weights, and that avoids uh, you know if you start with a weight that is more likely to be the correct answer, then you have to run the deep learning model for fewer epochs, and consequently your learning will be happen faster. Okay, then you have your momentum, which helps in learning by a fraction of previous update in the direction to overcome local minima. All right, we'll see what a local minima is when we learn gradient algorithms. Okay, so there's a thing called global minima, and there's a thing called global, local minima and global minima. Okay, global minima is the one that we want. That is where the weights, the errors is the minimum. Errors are the minimum, and local minima is, it seems like the we have reached the optimal solution, but it is not the case. Okay, what we want to do is we want to avoid local minima, and we want it to be our local global minima to be the answer. Okay, optimization algorithms like stochastic gradient descent, RMS prop adjust weights during the training. Okay, so optimization algorithms, once you calculate the error, these optimization algorithms help you to uh, converge to the actual answer in a fast manner. Okay, then what are the loss functions? When you take one run through the entire um, through the entire model, through the entire architecture, you have to calculate the losses, right? Either it is after a small batch, or it is through the entire batch, after the entire batch. So that basically measures the difference between the predicted output and the true output. Okay, very famous among them is the mean squared error, MSE, and that is used for regression tasks. So mean squared error is 1 by n summation of 1 to n yi minus y hat I, yi hat whole square. Okay, so say we have uh, two instances. Okay, in not gate, uh, in a not gate we only have two inputs, right? So the formula will become 1 by 2 into bracket, you'll have yi for y1 minus y1 hat whole square plus y2 minus y2 hat. Okay, so the actual value of y minus the predicted value of y for the first term, and added with the second value for y, actual value, and the predicted value for y as well. Okay, and after you sum it up, you will divide it by n, which is 2 in case of not gate. Okay, and that will be your mean squared error. All right, now you have the binary cross entropy. The binary cross entropy is used for binary classification. The formula is given as under 1 by, minus 1 by n summation of 1 to n, and y log y hat plus 1 minus y into log of 1 minus y hat. All right, so that is the binary cross entropy, which is used for binary classification. When you have a multi-class classification, you use categorical cross entropy, which is the summation of minus one, which is loss is equal to minus 1 by n summation of 1 to n and j equal to 1 to c, yij into log of y hat ij. Okay, where yij is the true label of sample I and class j. This is 1 for correct class and 0 for other, that is 1 hot encoding. Y hat ij is the predicted probability of sample I and class j. The output of softmax activation function, uh, output of the softmax activation function n is the number of samples and c is the total number of classes. Okay, so that's categorical and binary cross entropy. Data augmentation. Once you have uh, if this technique is used when you only have a limited amount of data and you want to increase the number of data points that you have. Okay, so that's data augmentation. This technique is used to artificially increase the size of data by creating modified versions of data, reducing overfitting. Examples of for images, uh, you perform rotation, flipping, cropping, add noise, brightness adjustments, and all those things. Okay, so basically, if you have a single image, you can make multiple images out of it by doing these operations on performing these operations on that image. Okay, uh, examples of text, you can have a synonym replacement, paraphrasing, random word in the insertion, and such. The benefits of data augmentation is it improves generalization by exposing the model to a variety of data. Okay, so in case you are having less data, what you can do is you can have data augmentation. Uh, Now we come to the activation functions. Okay, if you remember, we had activation functions written inside the um, circle. Okay, inside the circle we wrote the activation function relu. By their right. So what are activation functions? Uh, They introduce non-linearity and enable the network to learn complex patterns. So we have already seen this when we used ReLU for solving XOR problem, right? So ReLU introduced non-linearity. It bent the um, solution space and the input as well. Okay, and that is how we were able to once we had it in multiple layers, pass through the ReLU function first, then we had what we could solve the XOR problem very easily. Okay, so there are various kinds of activation functions. Sigmoid activation function, which maps the input to a value between 0 and 1. It is often used with binary classification. We have also used it uh, for, I guess, not example with not. Okay, not gate example used sigmoid activation function. It can cause the limitations is it can cause vanishing gradients for a very large or small inputs. Okay, then we have tanh, which maps the values between -1 and 1. It is similar to sigmoid, but it is centered around 0. Okay, ReLU is rectified linear unit. It outputs the input if positive, and otherwise it is 0. It's popular with deep learning neural networks because it is faster in computation and avoids vanishing gradients. Okay, so the formula for it is given by max of 0 comma x. uh, if you don't want your negative values to become zero, there's something called as leaky ReLU, which allows small slope for negative inputs to avoid dead neurons. Dead neurons is value is equal to zero. Okay. Then softmax, it is used in the input layer for multi-class classification. In outputs the probability distribution over classes. It converts the inputs into probability summing up to zero. Softmax function, activation function we use as the output in the output layer. Okay. When we have multi-class classification. Okay, and suppose there are 10 classes, and softmax, what it does is it gives uh, the output in such a way that if we sum up all the outputs, it will come to be 1, and the class which has the greatest value, the greatest probability or the greatest value, is the class that is the output. Okay, so with that we come to the end of our video over here. Thank you for everyone. We'll see in the next video.